Videos the A plus BI. Oh, we are live, and I'm asking a dumb question.
There are no dumb questions in quantum mechanics except for
All right, well, good.
We're live, boys and girls.
Again. All right, we are live, and oh boy, we're going to go over complex numbers and a little bit of what wave functions are. So, how do we begin? Well, I can't explain what complex numbers are without going over a few more basic things first. And those things are called real numbers. So, a few little facts about real numbers. So, first of all, with real numbers, they exist as a continuum, meaning that you have numbers like 0, you have numbers like 1, you have numbers like 2, you have numbers like 3, you also have numbers like pi. But an important property of real numbers is that there is no start or end to them, really. There's an infinite and uncountable number of real numbers. But real numbers also account for negative numbers, too, negative integers, like -1, -2, -3, -4, -5. So that's part of what real numbers are. And here's facts concerning real numbers. So the first fact is regarding the addition of real numbers. So if you have A and B, which are elements of the real numbers, then A plus B is also in the real numbers. And A times B, that's a large B. And A times B is also an element of the real numbers. Okay, good. So an example, just to kind of make this more concrete. Say A equals 2 and B is equal to 3. Well, A plus B is 5, and that's also a real number. It's over here. And A times B is 3 times 2, which is also a real number, times 6. So a graphical idea of what real numbers do is they either shrink or contract on the number line based on their value. So some rules regarding real numbers is, for instance, multiplication can be more tricky. But so if I have A and B, and I consider positive values of A and negative values of A, positive values of B, negative values of B, and then I think about their product, A times B, so I'll write that as AB. A positive times a positive number is positive. A negative number times a negative number is positive. And there's actually 2 more possibilities we can do here, which is, what about A being positive and B being negative? And A being negative and B being positive. Well, then A times B also would be negative, and negative number times a positive number will also be negative. So far, so good with real numbers?
Yep, I feel like I'm in
Good.
I don't know
Okay.
what they actually called these real numbers, but this is like, what, 6th grade math?
Yeah, so far so good. So most people will have heard of real numbers. Let me introduce the idea of a function. So the idea of a function.
You might mention closure. I don't know.
Right. So this property we named earlier about a plus b also being an element of the real numbers, and a times b also being an element of the real numbers, is something we call as a property of algebraic structures called closure. Closure under addition and closure under multiplication. But also, let's notice something interesting. And let's talk about real functions, and we'll study a very interesting example of a function in a moment. So first of all, I'll introduce what a function is. So a function of a real variable So first of all, when we take a function, we generally denote it as a function as some value of y is equal to some function of x, meaning that if I give you some value of x, you will obtain some value of y by some process. And so you can think about it as being a machine of sorts. What you can think about this being in general is thinking about that for every value of x that I feed into this process f, or into this function f acts on that variable in some way by process f of x, and the result that it spits out is some new thing called y. So that seems fairly abstract, and it is. So let's consider an example of a function. Let's say we take the value to be a squaring function, y equals to x squared. Well, let's think about a few values for this function. So let's think about the various values of x and various values of y that are the result of feeding x into this function. So let's say we do -2, -1, 0, 1, 2. So if I take a negative number and I multiply it by itself, it's going to be positive. And -2 squared is going to be -2 times -2, which would be positive 4. Negative number times a negative number is positive for the case -1 times -1. And 1 times 1 is just 1. So 1. 0 times anything is always 0. And 1 times 1 times itself is 1. And 2 times itself is 4. And so what we could do is we could graph this. What we could do is we could think about how y and x are related to each other. And this graph, what we would do is we draw a line. These will be our values of x. This will be our values of y. So -2, -1. This would be 0. This would be 1. This would be 2. And the highest value we ever hit is 4. So 1, 2, 3, 4. So -2, our value is at 4. -1, our function is at 1. 0, our function is at 0. 1, our function is at 1. And at 2, the value of our function is at 4. And so it looks something like this. And the general shape of this curve is called a parabola. And actually, there's something interesting which is happening with this. And that is, notice something. When we take values for x, what are the values of y that we're obtaining always? Scott, any idea?
I'm sorry, what?
Whenever we take a value of x, it doesn't matter what value of x. What are we always getting on the y?
The square of it?
Yeah, but in particular, do you notice something special about these numbers? The fact that they're non-negative, for instance.
Oh, yeah, they're all above the x-axis.
Right. So curiously enough, one interesting fact is that real numbers have a property that if a and b are real numbers, then a squared can never equal negative b squared. And what does that mean? Well, let's redraw ourselves a picture of our real line. So what this is saying, essentially, is if I take 0, and I take some value of a, and I take some other value to be b, well, what that's telling me is if I take a to be positive, or any value, a squared is going to be larger, unless a is less than 1. So this might be a squared. And b, even if it's negative, well, b squared is going to be somewhere positive as well. But what this is telling me is that no matter what number I pick out of the set of real numbers, I will never be able to have it be the case that a number I pick for a and square it, I can never get that to be negative. And so that's one of the special things about real numbers as a system. And this actually acts as a perfect segue to get into the idea of what are called complex numbers and the imaginary number. So first of all, the imaginary number. So the imaginary number there's a way back in mathematics, like the 17th century or so, people described a number which is different. And that is a number we call I, the imaginary number. And it has the definition that it's equal to the square root of minus 1. And if we square each side of this expression, we get that I squared is negative 1. Well, that's actually quite interesting, isn't it? Because this is the exact thing we were looking for that we were ashamed about from real numbers, that we can't have a square number be equal to a negative number. And this is the exact reason complex numbers were developed. Because it turns out that certain algebraic problems need this type of number to exist. Okay, great. So if that's an imaginary number, that's nice. It's a nice mathematical tool. But what does it really do for us? It doesn't seem to do much good. Well, first of all, complex numbers. So a complex number has something interesting happening with it. So a complex number is defined to be some number which has two components, a plus b times I, where both a and b are elements of the complex plane. We haven't talked about the complex plane yet, but we're about to. So, we mentioned already that I equals the square root of minus 1 and I squared equals minus 1 does something for us. But what does that actually do? Well, what it allows us to do is it allows us to expand our view of numbers. So it allows us to do this. We have a real number line already, and this exists as being the set of numbers we're already familiar with. So numbers like 0, 1, 2, 3, and so on and so on and so on. And we already said the boring news, -1, -2, -3, yada, 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 yada. Well, what complex numbers are doing now is they're extending this notion of real numbers into 2 dimensions. And what does that look like? Well, it looks approximately like this. So this is a point on a complex plane, 0, 0, and the units here are actually units of I, 2i, 3i, and so on and so on and so on. And and as a matter of fact, we can do the same thing going down. We have -I, -2i, -3i, -4i, and so on and so on and so on. Now, here's the interesting thing about it, actually, is when we take I to be the square root of -1, for instance. So if we take I to be the square root of -1, when we square it, it becomes negative. So curiously enough, this complex number that we have, when it's squared, it becomes real. Well, that's actually curious, because if we look at this graphically, this point is being I, and this point is being -1. What's happening here? Any ideas?
I don't know that I have the language to describe it.
Well, here's what's happening, actually. So if I take I and I multiply it by itself, I squared,
Uh-huh.
what's happening actually is that this point, so the important aspect of this, actually, is that multiplication by I, and this is actually something very instrumental to the idea of complex numbers, is that multiplication by I is the same as rotating rotating 90 degrees counterclockwise. Counterclockwise. So this is actually a very fundamental idea And actually, we can see this. So these lines all touch at 90-degree angles. And what's happening when we multiply by I, if you notice, this is an angle of 90 degrees that's being rotated by. And it's rotating it in the counterclockwise direction. It's rotating it in the whoops, that was not a very good counterclockwise symbol. But it's rotating it in the counterclockwise direction. This is something that I does to other numbers. And so, unlike real numbers that we've talked about, real numbers either cause some point to expand or contract on the real line, but multiplication by this I number allows you to rotate. And that's kind of nifty.
Okay.
Okay, we've talked about imaginary numbers, and we've defined what a complex number was, so the definition we gave of a complex number was that it's two combinations of numbers. It's a plus b times I, where both a and b were elements of the real numbers. So, okay. Let's try to think about let's try to do the same thing we did earlier in regards to the squaring process of a real number. So let's think about squaring real numbers again. So if we take two numbers, a plus b, and I square that, well, that means it's a times a plus b times a plus b. Okay, fine. And the way we multiply these numbers is the first two get multiplied, which we call first, or f. The outer number gets multiplied. The outer two number gets multiplied. So outer, or O. Then the inner two numbers get multiplied, which we call I. And last, we have two more numbers to multiply. The last two numbers, or the longest two numbers that are away from each other. And this process has a name. It's called
the FOIL method.
Right. This is called the foiling method, which stands for first, outer, inner, last. First, outer, inner, last. And the result of multiplication of these two real numbers gives us a times a, so a squared, plus a times b, plus b times a, plus b times b, or b squared. A times b and b times a are actually the same thing.
Mm-hmm.
And this gives us a squared plus 2ab plus b squared. And importantly, there's one last interesting thing about this. So earlier we said that we made mention of the fact that a plus b is a real number, and a times b is a real number as well.
Mm-hmm.
And actually, since we just performed multiplication, we can do a little bit better. A times a, that's real. A times b is real, and 2 is a real number, so this is also real. b times b, or b squared, is also real. So the entirety of this thing is also an element
Of the
of the
real set of real numbers.
Yeah. So whatever these two numbers are when we add them in square is also an element of the real numbers. Okay, fine. We've done that for real numbers now, so let's do it for complex numbers. So let's take some complex number z to equal a plus bi, and a and b, like we've said again, are both elements of real numbers.
Is that a 2 or a z there on the left of the equals?
Z.
Okay.
So z squared is equal to a plus bi times a plus
A-
bi, and a times a,
Yeah.
yep, a times a squared, a times bi, which is abi,
It's going to be 2 ABI
yep, so it's plus again, a
plus
times,
BI squared.
yep, so plus bai, which is the same,
Yeah.
these two are the same, plus I times b squared. Okay, beautiful. Now, I times I is -1, and so
Right.
this is actually negative b squared.
Okay.
So this equals, grouping real numbers together, a squared minus b squared plus 2 times a b I. And a squared minus b squared is definitely real. 2ab is definitely real, but this I is an imaginary number.
Mm-hmm.
And this means that this number is also an element of the complex numbers.
Right.
Since we have a real number and another real number times I. Great. Now, here's where things get a little bit more interesting. Let me introduce the idea of what's called a complex conjugate. So I will introduce the idea of what's called a complex conjugate. So if I have a number z, which is equal to a plus bi, then the complex conjugate of z, which I'll call z star, is a minus bi. And so what the complex conjugate is just doing is this I right here gets replaced by negative I. And that's all that happens.
The I on the right, the BI.
Yeah,
Okay.
precisely. So this I over here.
Now, why is it being called a conjugate?
So it's called a conjugate because graphically they look. You'll see what happens when you conjugate them, when you multiply them. It turns out that these two things are very special.
Okay.
So let's perform a slightly different multiplication. So it's obvious that z is an element of the complex numbers because a is real, b is real as well, and z star is also going to be complex because this is real and b is also real. Is also an element of the complex numbers. But what becomes curious about this is what about their product? So what about z times z star? Well, that's equal to a plus bi times a minus bi. And this becomes,
A squared
yep,
plus 0, essentially, right?
yep. So minus abi plus abi.
And then b squared I squared, or bi squared, yeah.
Yeah, so minus ib squared, well, I squared b squared. I squared is -1.
-1, yeah.
These two negative ones, turns out, these two negative ones, -1 times -1 is positive.
Mm-hmm.
And this becomes 0. So this just becomes a squared plus b squared. And actually, since a and b are both real numbers, and a squared is going to be real, and b squared is also going to be real since a and b are both real, a squared and b squared actually is a real number.
It's like Pinocchio becoming a real boy.
Oh, yeah. But this is actually rather fascinating. So when we take this interesting product of z with z star, we don't end up with something complex, even though z and z star are both complex.
Mm-hmm.
We get something real once more. Well, that's actually very good. So, before we jump into wave functions, let's cover the graphical interpretation of complex numbers. So, we've already mentioned that I can think about complex numbers as being some set of numbers that are on the imaginary axis and some set of numbers that are on a real axis. And I'll call this number A, for instance. And let's say the number I want to deal with, or the complex number I'll deal with, let me say that z is 3 plus 4i. Okay, so that means that for the I have to go up 4, and a, which is a real number, means I have to go 1, 2, 3. So I go up 3, or to the right 3, and I go up 4. So 1, 2, 3, 4. And my number will rest on this position right here. Well, okay, that's good. Now, we can think about that as being, we had 3 of something in terms of our real part, and we also had something being imaginary with respect to this part. So this part was 3, and this part was 4, and these are both these both don't need I, because the units for this y-axis on this 2D plot, the y-axis is in terms of I. So if I add these two, it will give me 3 plus 4i. So we can always draw a line between the origin and our x-axis, which in this case we've labeled A. And importantly, we can call this angle to be theta. That's fine. And as a matter of fact, in general, so a general statement is that when I have a number x plus iy, and that number lives on the complex plane. So this might be some number x, and this might be some number y, and this is the I, and this is some real number. What we can do now is blow this triangle up, so we can draw it as being that. And remember, the vertical this part right here, this horizontal part of it, was on the x-axis.
Mm-hmm.
This vertical part here was on the y-axis.
Mm-hmm.
We said we can incorporate an angle into this, which is fine. So we will. We'll call this angle theta. And okay, so what about this diagonal part? What are we going to do with that?
You mean we're going to call it a hypotenuse?
Yeah. What's this hypotenuse actually equal to? Well, to deal with that.
X squared plus y squared.
Yeah, precisely. So actually, by the Pythagorean theorem, by Pythagorean theorem,
H equal the... I can't remember the Pythagorean theorem anymore. This is how old I'm getting.
Right.
And plus, I never use that concepts.
Yeah, but so for the Pythagorean theorem, what it essentially states is that
square root of x squared plus y squared is, well, that's how you...
if you have two sides A and B, and this is a right angle triangle, and this actually is, because the x and y axis meet at a right angle, they meet at 90 degrees. Then what is true is the following. Then if you call this side C, then a squared plus b squared is equal to c squared. And in our case, this implies that c squared would be x squared plus y squared. Or taking the square root means that c is actually equal to the square root of x squared plus y squared. Okay, beautiful. And this completes our little triangle. So what we've learned about this process is that when I take two complex numbers, or when I take a complex number and I plot it, so x and y, and I draw a line from the origin to that point, what I've learned is that if I consider these to be units of distance, so some direction moving in the y and some direction traveled in x, then what I've learned is that this distance is actually the square root of x squared plus y squared. And that's actually rather useful. So this actually is why complex numbers are treated as vectors in a way. Because why? Well, vectors, first of all.
I hope Tangelo's listening.
Right. So vectors have magnitude.
And direction.
Yep. Have magnitude and direction. And the way we depict that actually is with an arrow. So, and notice, when we take something like 2 plus 3i, or 3 plus 4i rather, and we graph it. So this is the real axis, and this is I. 3 up 4. We actually do have a vector of sorts because our numbers are positive, and so our x jots along this direction. It jots in the positive. Our x value is positive, and it goes to the right. And our y value is up and positive.
Mm-hmm.
And in that way, actually, because these arrows exist, because there's a kind of directionality here, these complex numbers are actually very similar to the idea of a vector. And it satisfies some nice properties that if you choose to learn more about, will become quite interesting. But here's the important aspect of that, is that there's a formal way we can define this. So we remembered that when we had something like x and y, and this being some length z at an angle theta, we can save ourselves some space by drawing this again. So it'll be here, up, and then there.
Are you depicting z as the hypothesis or a z-axis? Okay, just
right. So this is z as the hypotenuse, and this is x, and this is y. As a matter of fact, what we can do, always as being the case, is something fun. So we can say that z, using trigonometric functions, we can say that z is x cos, let's see. So z is y sine theta, and z is also x cosine theta.
Now, it's been a while since I've had trigonometry, but
right. So let me.
These are basically adjacent, tangent.
Right. So let me.
Okay.
Right. Let me give the audience a little bit of an idea of what this is. So when we draw a triangle, and we have some angle theta, like say this is A, for instance, what we imagine, is we draw a line from where theta is until we hit a wall here.
Mm-hmm.
And we call this the opposite side.
Okay.
And the line that's directly below that, so this part right here, is called the adjacent side.
Adjacent, okay.
And our cosine theta.
This brings back memories.
Yeah, and it turns out that, well, let's call this B and let's call this C so that we have some idea. This is called, as you correctly pointed out, this is called hypotenuse. So it turns out that sine theta is the opposite side over hypotenuse. And cosine theta is the adjacent side, divided by the hypotenuse. Now, these are tremendously useful and very widely encountered in quantum mechanics.
Mm-hmm.
There's a reason we've chosen to introduce this. And that is, remember that our z value, as we defined it originally, so z being some complex number, takes the form x plus iy. Well, remember, this actually means something rather interesting. And that is, what we can do with this is actually rewrite this. And actually, what this will do is we will obtain that x cosine theta. Well, what we will obtain, essentially, cheating a little, is z is actually cosine theta plus I sine theta. So actually, what we can do is, when we have two values and we choose to introduce an angle, right? Our components of z can be directly expressed by x times cosine and I times y sine of theta. And that's a rather useful thing that we'll encounter in future installments of this. But for now, let's actually talk a little bit about quantum mechanics. So, why in the world did I go through all this nightmarish stuff in regards to complex numbers and real numbers and all the like? Well, here's why. The first thing to know about quantum mechanics is that, well, the very first thing to know about quantum mechanics is a wave function takes on a variable which has the Greek name psi, and this stands for the wave for properties of it stands for some function which solves the Schrodinger equation, which we'll also talk about a little bit later. But for now, a normalization criteria. So a normalization criteria. So normalization condition. Well, here's what the normalization condition states. That of magnitude and that might seem a little bit weird at first, but let me try to explain what it actually means. So the first thing to note about psi, this wave function, is psi is complex. And this magnitude of psi thing, well, how can we rationalize that? Well, if you remember this picture we were talking about in terms of x and y, and how we're trying to define z in terms of it. Well, what we can do is this. Let's relabel some things. So let's draw our complex plane again. And this would be some value of psi in the x direction. There's some point in the complex plane we want to touch. Some value of psi in the y direction. We have an angle theta. And this thing we called z earlier, because remember, we called this thing x and we called this thing y. Another name for z that's given in complex in the treatment of complex numbers is this. Is this symbol with these vertical lines around it. And this reads, this vertical symbol reads the norm of something. And so when we put something inside of this, we're asking for the norm of it. And the norm,
it kind of looks like the absolute value symbol
it
too.
is. It
Oh,
is.
it is. So the fancy way of saying absolute value is to say the norm of.
Yes, in complex numbers, they call it the norm.
Okay.
And this norm, actually, so this norm of psi is equal to the sum of its components squared. So it's this thing squared plus this other thing squared. So it's the value. Oops. What's happening here? The value of psi in the x squared plus the value of psi in the y squared, all surrounded by the square root. And that's quite similar to what we discovered earlier, being that for two numbers, x and y, this value z that we had was square root of x squared plus y squared. And this thing we're calling psi is no different. But remember, actually, an alternative definition we can give for psi, because psi is a function, we can also describe this as we can also describe this as being the square root of psi times psi star. Okay. Well, we know that psi times psi star is real, and we also know that psi x and psi y are going to be real as well, because the components of a complex number are real. Now, this thing we're dealing with, this integration, which I haven't explained what that means, asks us to do this. But given that we know what this thing is, we can rewrite it as square root psi star squared dx, and the square root and the square cancel each other, and just becomes that. Well, okay, that doesn't exactly tell me what it means, though. Well, that's a little difficult to do. But let me explain it in this way. Let's imagine for a moment that I have a box. So let's imagine that I have a box. So let's imagine that that there's a box here, right? And let's imagine that within this box lives a particle. And this particle is moving like crazy. It's moving near the speed of light. So at one moment it might be here, another moment it might be there, another moment it might be there, another moment it might be there. What this thing is telling us, actually, what this symbol means is it's asking about the area. And the area of what exactly? Well, this is asking about the probability. It's asking about the probability of finding something. In this case, it happens to be referring to finding the position of an electron or some elementary particle in space. And similarly, what we could think about is, if I were to ask you, Scott, or Speed, for instance, where is this particle at any given point in time? Well, because it's moving so quickly, you might not be able to tell me the answer to that question immediately. But the answer had better be somewhere within this box, somewhere within the confines of this box, right?
Yes.
So, in the same way, right, what this thing is doing, actually, what this thing tells us is actually that the position, or what this thing actually expresses to us is that the position or rather the probability of measuring a particle over all space must equal 100%. And actually, we can express this mathematically more uniformly. So,
Now, by all space, you still mean the box.
right, or whatever our confines are.
Okay.
And so in quantum mechanics, what this means is that the area, the likelihood of finding this particle, which is governed by this wave function, psi times psi star, over the entirety of the universe must equal 1. So when I look for this particle, when I look for some particle everywhere in the universe, there must be some place where this particle exists. And psi, or rather, the square of psi, tells me about the probability. Great. All right, so what is psi exactly? We've talked a lot about psi. We've talked about the fact that this weird area thing we're doing with psi must add up to equal 1. But what is psi itself? So psi is a function essentially that describes mathematically all the properties, or rather, that describes all measurable properties of some particle. Okay, beautiful. So, as a matter of fact, psi is a function that tells you essentially, it's like a cheat sheet. Psi embeds properties about the spin of a particle, about its charge, about its momentum, about its energy. It tells you all sorts of things that you would love to know about some particle of interest, like an electron or proton or quark or whatever it might be. And the other important thing about psi is that when we consider psi, we consider it to be a combination of functions. So it might be some function a of x, which is unknown, plus some other function b of x, plus c of x, times yada, 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 yada. Great. Well, and here's the thing about this, is that a constant times a function is still a function, it's just modified. And we can call these C1, C2, C3, and dot, 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 dot. And what we said earlier about this thing, about this being squared, because remember, this is equal to the magnitude of, this is equal to the sum of the area over the entire universe of the magnitude of psi squared has to be 1. And actually, what this means, this property of the wave function, what these numbers describe, so c1 squared plus c2 squared and c3 squared and c4 plus dot 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 equals 1. So what this describes, as a matter of fact, is what this thing describes, the c1 value squared, is probability of finding particle at of finding the particle at some position. At some position AX. And likewise, this corresponds to A2, or rather, we called this B of X, and so on and so on and so on. And the important takeaway here is that these constants which multiply with these functions, because you're allowed to have those for differential equations, the square of these numbers relate directly to the probability of finding a particle. And the last thing we'll cover is something akin to the notion of superposition. And the idea of superposition just asks about, is essentially a question about combination. What it's asking us is, how many ways could we combine a certain number of things to reach a certain state, to reach a certain value for a function? It's very hard to precisely describe what that means without going too heavily into the mathematics into it. And that's not what I want to do. But what I will tell you, what I will give you as an analogy is something like this. Imagine we roll two 6-sided dice, right? So each die has 6 sides, and the other one also has 6 sides, right? And each die has a number associated with each face of the die, and we can actually think about that. So you can think about die 1 has has values 1, 2, 3, 4, 5, 6. And die 2 has values 1, 2, 3, 4, 5, 6. And actually, what we can do is we can think about, let's play a little game. Let's add the values that these dice can have. Right? So let's actually take the sum. Let's take 2 dice, let's roll them, and let's think about the numbers that we can have. So the range of numbers we can have are 2, something, 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 to 6 plus 6, which would be 12. Okay, well that's nice. And the game will play, as a matter of fact. The way we'll relate this to superposition is thinking about each of these states of this combined dice roll as being unique. And what we'll do, actually, is we'll give a number for each of these. So we'll put 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And we'll count the number of ways that we can count each of these. So, for instance, the number of ways, I could count, the number of ways I could get 2 by rolling 2 dice with 6 sides. Well, I can only do that in one way.
Snake eyes.
Huh?
Snake eyes. 1 and 1.
Precisely. 1 and 1. 1 and 1, rather. For 3, actually, there's 2 ways I can do it. And those 2 ways are adding 1 and 2, or 2 and 1. Okay, fine. Now, 4, there's many, many more different ways I can do it. But, for instance, one of them would be 1 and 3, 3 and 1, and 2 and 2. Right, so there's exactly 3 ways that I can do it for 4.
Mm-hmm.
And so on, 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 and so on. Right? And as a matter of fact, if we think about the middle number here, which should be the point of this exercise is that I can keep listing numbers of ways to do this. I could get 1 plus 4, 4 plus 1, 3 plus 2, 2 plus 3. Right? And that would actually give me, this would give me 4 ways. Because I could have 1 plus 4, 4 plus 1, 3 plus 2, 2 plus 3. That would be 4 ways. Let's do it for the rest of these really quickly. So we could do 1 plus 5, 5 plus 1, 3 plus 3, 4 plus 2, and 2 plus 4. And the number of ways that gives us is total 1, 2, 3, 4, 5. 5. All right, what about the number 7? Well, let's see. 1 plus 6, 6 plus 1, 5 plus 2, 2 plus 5, 3 plus 4, and 4 plus 3 are all different ways that the combination of 2 rolls on a 6-side die can give us. And this is 1, 2, 3, 4, 5, 6. For 8, it's a little bit rougher to think about, but let's erase these for a moment to give ourselves some room. So we could think about this as being 2 plus 6, 6 plus 2, 5 plus 3, 3 plus 5, and 4 plus 4. Right, so this gives 1, 2, 3, 4, 5. And as a matter of fact, it turns out, and I won't show this for the brevity of time, So it turns out there will be 4 ways to do this, 3 ways to do this, 2 ways to do this, and 1 way to do that. And I'll leave you to think about that.
It reminds me of a parabola or something.
Well, what this should remind you of is if we were to plot this, right? So if we were to think about this in terms of distribution, so we think about the value. So let's think about this in terms of say value, or rather, let's think about this as the sum of 2 dice. And think about this one as being, for instance, the frequency. So frequency of each number. Well, the highest we get is 6, and the lowest we get is 1. And so you get 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 1 is at 6. This is going to be 5, 4, 3, 2. So the distribution, if you really are kind of quick about drawing it, it looks like this, or rather 2, and there's 5 on this one. There's 4 on the next one. 3 on this one. 2 on this one. 1 on this one. But the idea is that if you were to plot this correctly, what you would actually, I'm sorry, I drew this incorrectly. That was a stupid mistake. So what you would actually notice is that what we said earlier about 7 being the highest. 7 is in fact the highest number. There are 6 ways to represent it. For 2, there's only 1 way. For 3, there's only 2 ways. For 4, there's only 3 ways. For 5, there's only that number of ways. And so on and so on. The rough picture you'll get from doing this kind of sampling process is something which looks like a bell-shaped curve. And actually, as a matter of fact, what's significant about this is much in the same way, right? What we're talking about with dice is how many is for the combinations of dice. How many ways could you have got there? How many ways could you have added the dice to hit some number? And in our case, we considered the range of numbers 2 through 12. Quantum mechanics does something different. It tells you about if you have some final area you want to get to. So if your point is on the number if your point is, again, say for instance, 3, 4, right?
Right.
What this idea tells you, what this notion of countability is asking for, and what superposition fundamentally is doing, is it's trying to ask you, instead of just representing this by, the vector 3, 4, which this would be, up 4 and over 3, maybe you could do it in different ways, right? So that's the idea of superposition. In much the same way with dice, that you're asking about how many ways can you sum to a specific number. The idea of superposition is thinking about when I combine these two vectors. So when I combine this vector that moves in the direction of x at 3 units, and I combine it with a vector that's moving up 4 in the vertical direction, I get a vector called 3, 4. But that's not the only way I could have arrived there, for instance. And next time, we'll go a little bit more into quantum mechanics and explore this concept a little bit deeper about what superposition is, this idea of re-representing our vectors, and maybe touch on the idea of why wave functions are actually significant and what wave function collapses.
Sounds like a plan.
Yep. Anything that was of clearance, or
Well,
needed more work?
in terms of the symbols being used, that asterisk, what was it again? What did it represent?
Conjugate.
Conjugate. Okay.
Yeah. All right. Well, guys, this has been fun. We've been going on for a while, and my computer is starting to hate me for using it for so long. So we'll see you soon. Take care.
I hope it doesn't melt.
I'll kill it if it does.
Have a good one.
Yep. Take care.